Problems in physical theories. Because people treat particles like electrons as point particles, there are problems when you talk about the Coulomb potential. As R tends to 0, this tends to infinity. So there are no such things really as point particles. Particles have dimensions, but people tend to disregard that, especially in developing field theories. In particular, string theory complements itself on being the first quantum theory ever to include gravity without also including ultraviolet divergences. I don't think it's particularly significant to string theory. Other theories have also been developed. Problems have arisen in non-relativistic quantum mechanics. For instance, the problem of treating a particle in a box where you have a plane wave solution of this type with an constant amplitude. The probability of finding the particle after any time t equal to 0 would be the conjugate multiplying the wave function by its complex conjugate, which would be a e divided this cancels with that, and therefore is a constant probability to find the particle anywhere. And this is not physical, because if I know the particle is located at a certain point, at a certain time, the probability to find it afterwards, being anywhere in the universe, doesn't seem like it's a logical consequence. This is called non-locality, and it's due to the fact that we go to the non-relativistic limit. Another problem is dealing with wave velocities. In non-relativistic quantum mechanics, you don't have c, the velocity of light. So there's a possibility that the particle can have any velocity it chooses. There's no limit. So the idea is to determine fundamental lengths, masses, and other quantities based upon the constants c, h bar, e, and E is charge, G is Newtonian potential, H is Planck's constant, and C is the velocity of light. I group these four constants into different groups, H and C, E and G. C, the velocity of light, meant that time was no longer absolute. In Galilean form, I have the transformation from one inertial frame to another, but with t equal to t prime. The introduction of C meant that time was no longer absolute. The introduction of h bar meant that energy is no longer continuous. In fact, it is given in terms of quanta of energy. So these constants put limitations on time and energy. These constants, rather, E and G, determine the strengths and the potential. I can form a number, dimensionless number, which is E squared divided by CH, which is called the fine structure constant. Okay? Is equal to 1 over 137. Because of its smallness, we can do perturbation theory using this constant. Okay? This attests to the fact that in electromagnetism, there is you can expand the potential in terms of alpha, and we'll do so for the hydrogen atom. The the fact that we can use this constant to determine characteristic lengths, but we cannot form any type of combination of h, c, and e squared to give us length. Length doesn't exist, and if length doesn't exist, neither does mass. And this means in electromagnetism that the propagation of electromagnetic waves are not damped. There is no limitation on their propagation. Okay? They can propagate infinite distances. There is no mass or no length. So if we start with the classical radius of an electron, we would obtain an expression by equating the rest mass to the Coulomb potential, and we would come up with a classical radius of this amount, which is quite small. If we multiply this by alpha to the minus 1, which is equal to e squared over c squared, e squared over hc, the charge cancels, and we come out with the Compton wavelength. Okay? It is still relativistic, but charges disappeared. So every time something disappears, means that it's out of the domain of validity. Okay? Here, for the classical radius, why I call it classical? Because h bar is missing. This is beyond the domain of quantum mechanics. This is the Compton wavelength, which is the smallest wavelength that can be used to form a packet of waves to describe the localization of an electron. If we do this again, multiply by 8 to the minus 1 of the Compton wavelength, we come out with this becomes squared. This doesn't exist. And we get h. Another characteristic wavelength. Okay? Here, C has disappeared completely. So we know that we're outside the domain of relativity. It is still quantum oriented because of the h bar. And this is called the first Bohr radius. If we multiply by n squared, we get Rn. Okay? So these are the three characteristic domains that we have. Every time a universal constant disappears, means that we are leaving that region of its domain of validity. So these are the three characteristic wavelengths. We can do the same thing using Gm, m is the central mass, instead of E squared. Okay? But here's the problem. We can form now, using G, means that we can form a mass. We can combine the units. This is called the Planck mass. And we can form the wavelength. And we can introduce mass. What is surprising here is that the range of the extent of the range of interaction of gravity implies that it is not infinite, because there is a characteristic length which is a Planck length. We can define a Planck energy like we did last time, deriving the black hole, what they call a black hole entropy, and therefore it should not be infinite in extent. Surprisingly, general relativity claims that gravity propagates with the velocity c. Just like electromagnetic waves, photons are weightless. Gravitons shouldn't be. So the whole problem is that if we release the idea that we can, of causality, then we can start to have theories which are finite. that do not give infinities. Infinities come about because we go to the limit. Interesting enough that Erwin Schroedinger, serving in the Austrian army during World War I, was sitting in a trench and musing about the idea of should we go to the limit. And he wrote, "It is, so to speak, part of the creed of the atomist that all partial differential equations of mathematical physics are incorrect in a strictly mathematical sense. For mathematical symbol of the differential quotient describes the transition in the limit to arbitrary small spatial variations, while we are convinced that in forming such physical differential quotients, we must stop at physically infinitely small regions." Why was he thinking about these things? He was working on the heat capacity, a model of heat capacity with von Karman, in which the heat capacity was a string. He was trying to determine the heat capacity for a one-dimensional string. And there you couldn't go to the limit because the atoms are placed regularly along the string. So, thank heavens though that he changed his mind 12 years later when he derived his equation. Okay? So the problem is that with non-relativistic theories, you get things like nonlocality, the propagation of the velocity, the speed of velocity of the particle can be infinite, and these are problems precisely when you go to the limit. Okay? So now, what I want to do is to derive the Schrodinger equation, finite difference equation, show that it contains relativistic effects when you do not go to the limit, and compare this with relativity. And all of this amounts to is the passage from hyper-bolic geometry to elliptic geometry is by allowing the radius to become imaginary. And if we allow certain quantities to become imaginary, we make a very clear transition from a diffusion equation to a Schrodinger equation, which propagates. Okay? And I think the most easiest way to go about it is to start with a one-dimensional model of a particle making a transition on a line. Okay? We have certain points where the particle can make a transition to. Call this R, R plus 1, R minus 1. Okay? So if a particle is sitting in R, it can make a transition to R plus 1 in T, delta T, which is a small time. It can go backwards. The particle can retrace itself and make a transition in the same delta T, or it can go to R in K prime delta T, and this way again, K prime delta T. Okay, so the particle can jump back and forth from one side to the other, and there's a continuity equation, it's called the master equation, which if P is the probability of finding the particle at site R, it is equal to K P L plus 1 minus 2 minus K plus K prime P of R plus K prime P of R minus 1. Okay? So this says that a jump from R plus 1 to R will increase the number of particles. It will be depleted by the jumps to the other two sites, and it will be increased again in this. And we want to solve this equation. But it's easier to solve a similar equation dealing with a what they call a generating function, which is given by that from r goes to minus infinity to r to infinity. Okay? This is called a generating function. You've probably come across the generating function in statistical mechanics, and the special name there, the partition function. Why do we use the generating function? It's easier to determine the moments. If I know all the moments of probability distribution, I know the probability distribution itself. So by determining the moments, I get information on the form of the probability distribution. So in order to do so here, I multiply both sides by z to the r. Okay? I can put z to the r inside, because it doesn't depend upon time, it's a dependent variable, and I come out with the equation dt equals kz minus k plus k prime plus k prime g. This is a linear differential equation, and it can be integrated immediately. And what we're interested in is the logarithm of g, which is equal to kz plus k prime over z minus, this is all times t, and this is k prime plus k t. Okay? So that's the expression I come out with. Then, if you go to the mathematical literature, you can see that this defines the generating function of what they call a modified Bessel function, which is e 1/2 z plus 1 over z tau equals r equals minus infinity to infinity times r tau by z to r. Okay? It's these two terms. If k is equal to k prime, I come out with something like this. And the form of the modified Bessel function, this is I1, I0. The increase is exponential with distance. Okay? Now, we can use log g to determine the characteristics of this equation by differentiating with respect to z, and since z is a dummy variable, we can set it equal to 0. So the first derivative is equal to k minus k prime c squared t. When I evaluate this at z equals to 1, because it is a dummy variable, I get this, k minus k prime t. And this is nothing more than the first moment. This tells me, is it more likely on the average for the particle to make a transition to the left or to the right? That depends upon the rate constants being unequal. If the rate constants are equal, then this is equal to 0. The particle is equally likely to make a transition to the right or to the left. So we shall put the rate constants equal to 0. The particle doesn't show any preference to transition to the left or to the right. And we go ahead and differentiate again. This is equal to 2 k prime z cubed t, putting z equal to 1, 2 k prime t. And this is equal to to L minus M, mean average squared, average, mean squared deviation. Okay? Now, this can be considered an average length, and if it is, the square of the average length is proportional to t, which is the finger mark of Brownian motion. Brownian motion has paths which are continuous, but not differentiable. When I go to the limit of small times, blows up. The closer the higher I make the magnifying glass, the magnification, the more irregular the paths become. And this was first developed, this theory was first developed by Einstein in 1905 for Brownian particles, where 2k is the diffusion constant. So taking the moments tells you that in the limit, this will become a diffusion equation with a diffusion constant equal to 2k prime. Okay? This is what we can say about the diffusive character of a particle. That means that if I look at Brownian particles as an ink drop in a glass of water, it will diffuse in time, and the black spot in the middle will become all gray. So in the end, everything becomes homogeneous. Okay? This has the appearance also, if I divide by some delta r squared and multiply by delta r squared, this becomes nothing but the finite difference of the second derivative. So in the limit, I will have dp in dt equals d. And this was the first, this was the equation Einstein started off with. D is the diffusion coefficient. And what he obtained was a characterization of the diffusion coefficient in this manner. And from this, he predicted molecular dimensions. If I add an I, square root of minus 1, imaginary constant, instead of spreading out, it becomes periodic. Okay? And this then, instead of P, I can't talk about a probability any longer, because I have something which is complex at least. So I have to go from a probability to an amplitude. Okay? And this is the passage from a real diffusion equation to the Schroedinger equation. Okay? And D, we know what D is already. If I have a world in which H is negligible, like our world, D tends to 0. As the mass of the particle grows, it no longer shows wave properties. It becomes a mass just like a table, which shows no wave properties. So D is a measure of the wave properties of matter, of an electron. Okay? Now, it's interesting to know that mathematics parallels physics, or physics parallels mathematics, because instead of dealing with a Bessel function, a modified Bessel function, if we introduce an I here, we get a Bessel function, J, of tau. And more specifically, what I get here is that if I use Z is equal to I to the theta, okay? And for Z to the minus 1, e to the minus theta, this becomes e to the cosine of theta t, okay? Which I will show later is related to the relativistic energy. If I introduce I theta, I come out with e to the cosine of theta. Then I have this coefficient beforehand, in front, which I will call omega t I. And I have this term, which is left over, which is a -1 here. And this is the generating function for the wave function R, which is J R omega tau. Okay? And if this differs from that with the introduction of this term here, so I will write this as the wave function itself. Okay? And what I have here is just nothing but a Fourier transform to obtain the generating function. Now, what I can do is to derive an equation from this. How do I do that? I differentiate with respect to time on both sides. Okay? And if I do that, I will come out with the form of the Bessel functions are periodic, decreasing periodic. So what I've gone is from a hyperbolic to an elliptic form, where I get periodicity from this. So I derive this with respect to t, equate equal powers of e to the I r on both sides, and what I do, I come out with is psi of r t equals I omega lambda squared divided by 2 if I take the limit where lambda is the spacing between r and r plus 1, when it goes to 0, I will get a second order derivative here, but it differs from this in the fact that it is now imaginary. And I must demand that this be equal to h bar over m. Omega hat is then equal to h over n, h bar squared over n squared c squared. This cancels with this. And this is nothing but the rest energy divided by Planck's constant. Planck's constant is energy per second. So this has the dimensions of frequency. Okay? And this is nothing more than the free particle equation, Schrodinger equation. But I haven't let delta lambda go to 0. Okay? And this will have important consequences. So, if I do an inverse Fourier transform on this, I can come out with psi r equals to e varying as, I should say, omega t cosine of theta minus 1 minus I r theta. Okay? I have a sum of all these things. But the sum now is that since I have I in exponent, these waves will interfere with one another. They will superimpose, or you'll have destructive interference. Okay? We don't be interested in destructive interference because that means that the particle is not there. So, if we want to go to the class, we should start off only with second order terms, not first order terms. Okay? because first order terms will give us problems. So I can call this e to the I s over h. Okay? Where s is an action. Action, remember, is the same dimensions as Planck's constant, and its variation with respect to h, size with respect to h, will determine the amplitude of the path. So s being equal to the closed line integral of momentums and a coordinate was precisely, in the old days, the only way that they could obtain quantization, h. Okay? For instance, if p is the angular momentum, q, the coordinate, would be the angle, and the closed path would be from 0 to 2 pi. This would be equal to n h. n being the number, integer number. Since angular momentum is conserved, I can take it out of the integral. This integral becomes 2 pi, and this is equal to nh, or L is equal to nh. This is the way Bohr used to quantize the angular momentum of the particle, the electron, around the proton. So this is nothing more than quantization. So here, what I'm interested in is getting S stationary. So stationary respect to what? Stationary respect to theta, for instance. So I write S equal to h bar omega p cosine theta minus 1 minus pi theta. Okay? Taking the first derivative, ds in the theta equals minus h in here. S will be equal to 0. Because we should remember what omega tilde is, and we come out with sine of theta equals r over t r over t and this we will call the ratio of the velocity to that of light. Okay? So instead of getting a velocity which is increasing or decreasing function, we get it as a circular function. Okay? And we can replace here for theta, we come out with I minus 1 all this to the exponent, and this is theta, sorry. And this is the expression for the wave function. If I take now the action, the derivative with respect to time, I come out with which is equal to multiply by h bar minus this, and this is equal minus the energy. Okay? So I have an expression now for the energy. And from this, I can also determine the first order term corrections to the energy of the hydrogen atom, which I will do. Okay? So, the easiest way to derive the expression for the velocity in terms of the Bohr atom is to use what they call a virial theorem, which says twice the kinetic energy is equal to a constant multiplied by the potential energy, which in this case is E squared Z over R. Z is the atomic number, okay? Then I can divide through by C squared, and here I have MC squared, and this is expression for beta squared. What I'm interested, though, is in the stationary orbits. That is, the proton is here. You get the circular orbits for the Bohr atom. This is n is equal to 1, n is equal to 2. So I want the expression for the nth orbit here. And if I do that, I come out with simply the expression we had before, introduced, and we come out with omega equals 1 minus square root minus b squared. For small velocities, I can develop this into a series, and I get this cancels with this. I multiply by h, and this becomes the energy. This term should give us the Rydberg energy. And this was precisely Bohr's proof that his model worked. He obtained the Rydberg energy, which was, at that time, just an experimentally determined quantity in terms of h, m, e squared, and z. Okay? And if I introduce this into here, I come out precisely with n squared plus 1/4 where R is the Rydberg energy expressed in terms of the fine structure constant. That's the Rydberg energy. That's 13.6 electron volts. That's the energy necessary to ionize the hydrogen atom. Okay? Which is this. This is all Schrödinger would give. Since we have not gone to the limit of a differential equation, we get other terms. And this term just happens to be the fine structure constant that Sommerfeld found by making an error and compensating the error by not knowing what spin was. And he came out with the first order correction. What he did precisely was the change in the energy is equal to alpha squared r into the fourth n j plus 1/2 minus 3/4. This is what he found. J is the angular momentum quantum number, J plus a half is the azimuthal quantum number that Bohr introduced. And for the maximum angular momentum, this is equal to n, a circular orbit. This gives me 1. 1 minus 3/4 is a quarter. And I come out precisely with that. Okay? So that's interesting. If I don't go to the limit, I start getting correct terms to a non-relativistic equation. Why non-relativistic? Because I have alpha appearing here. Alpha, if we recall, is E squared divided by H bar C. So we get relativistic corrections if we don't go to the limit. Okay? Any theory which gives up knowledge of causality, that means that by introducing lambda here as a spacing, lambda is H over MC. I am giving up any information about what happens between the lattice points. I know the particle will jump here, but I can't say how it's going to jump. This is lambda. And if I give that up, I start getting corrective terms. I give up causality. I'm introducing a minimum length. Okay? And this is logical, because if the electron does have some type of form, which today is still a point particle, then if it is hit by a photon coming in, there will be a finite time necessary, if d is the diameter and c is the speed of light, for the impulse to arrive at the other side of the electron, so he will move. It's not instantaneous. So if particles do have sizes, we have to reanalyze what goes on inside a certain wavelength, and we come up with corrective terms. Okay? We can even say more about this. What type of correlations there are between sites. Say if I have R plus 1 and R. How are they correlated? Okay? That means that if an impulse passes R, when it passes R, what's going to happen to R plus 1? Okay? Correlations. So we know that if we are at, say, site Q of R plus 1, it should be related to Q of R by a phase factor, theta. Okay? Now, this goes back to Feynman's model of electrons shuttling back on a lattice at velocity c. The possibility a turn to the right would be I over 2. A turn to the, this would be probability amplitude of a turn to the right. Probability would be a turn to the left would be minus 2. I over 2, which is just, this is just I, and this is just minus I. But if the particle is to remain in the same motion, we have to include plus theta, and if theta is equal to pi over 2, this will be e to the 0, which is 1. So the particle will continue in its path. So introducing minus pi over 2 here, we know pi, theta, is equal to, where is it? This is equal to and this is equal to nothing but this is Q of R, and this is Q of R plus 1. Okay? And this tells me how the transition is going to make from Q of R to Q of R plus 1. If I want it from 0, I have to introduce r here. But notice this, that minus the cosine of the inverse cosine, r cosine of beta is nothing but the elliptic distance on a sphere between 2 points. So here I've introduced the notion of elliptic distance on a sphere. Okay? And that provides me, I know that the geometry associated with this is elliptic. Okay? Now, what's going to happen if we don't put the I in and leave the I out? We know a sphere undergoes rotations. So I can write a rotation matrix, cosine of theta, minus sine of theta, sine of theta, cosine of theta, for x, y, and this will give me another point x prime, y prime. Okay? It's a rotation matrix. Looking at x and y, a point here, which is cosine theta, sine theta. Then we'll go to another position here, of minus sine theta, cosine theta. So I have a rotation counterclockwise. Okay? Now, since we're used to changing angles for imaginary angles, I can make theta imaginary, like I did before. I had e to the I theta, and e to the theta. And if I do this, I come out with cosine. About cosine, I sine, about sine, minus I sine theta, cosine, about cosine of theta of x. But I have an imaginary unit here, so I got to get rid of it somehow. So instead of introducing y, I introduce I times time. Ct is same dimension as x, and here I have prime. And you know what you call this? This is a Lorentz transformation. I can write it as x prime is equal to x cosine theta. I times I is negative, it's positive, plus ct sine theta. T prime is equal to x sine theta. I have an I all over, so I can cancel it, plus ct cosine. And that is nothing but a Lorentz transformation. Now we have to express theta can only be a function of the velocity. Okay? Remember, this is an inertial system. Dividing x prime by t prime, I come out with a velocity. And this is just, so in a certain sense, theta must be a function of velocity. So we have two inertial frames. One, say the k frame. K is moving with the velocity, with a given velocity, we have to find. And k prime is stationary, so if I divide in two, I will have v prime. Before I do that, I will say that I want to sit at the origin in the k frame. I put this equal to 0. So x prime becomes ct sine of theta. t prime becomes ct cosine of theta. I divide the two, and I call v prime equals this should not be here. This should be c here. So what I have is c hyperbolic tangent of theta. Okay? This is interesting. If we go back more than 200 years, a Russian called Lobachevsky came out, and defined a segment of a straight line as hyperbolic tangent. Okay? Now we are in velocity space. This is the velocity that I would measure from a Euclidean standpoint. If I look at theta equals tangent inverse of v prime over c, okay? And I use the fact that this is equal to 1/2 logarithm of 1 plus v prime over c divided by 1 minus v prime over c. And theta, e to the theta, is nothing but and we all know what that is. That is nothing but the Doppler effect. Okay? So if I do the same thing here, look for the correlation between q of r plus 1 and q of r. Here I have e to the theta, which just means that it is Doppler shifted. And if I take it at the origin, r, this will be r times Doppler shifted. So here, when I get a phase factor, which is the distance in elliptic space, here I get a phase factor, imaginary phase factor, which is just a Doppler shift. So I know that these two come from two different worlds, an elliptic world and a hyperbolic world. And what I said to you at the beginning was that to transfer from elliptic geometry, which is spherical geometry, I use an imaginary r, the radius, I r. And from this, you can derive special relativity on one hand and quantum mechanics on the other, just by making the angle imaginary. Okay, we know one other point is that this theta I can write as c tangent over c. This again is proportional to the velocity, as I said at the beginning, but this velocity is different from this velocity. This is what a Euclidean person would measure. This velocity, recall that v prime, as v prime goes to infinity, this will become infinite when v prime is equal to c. This is bounded by c. This is not bounded at all. It can become infinite. So maybe those people in the Grand Sasso that were measuring, they were measuring this velocity and not that one, which has no bounds. In this space, c is a constant, an absolute constant. That means that to us Euclideans, we need the Bureau of Standards. If you took the if you got rid of the Bureau of Standards, we wouldn't know what a meter is. How do you define a second? We need these things because, in this sense, Euclidean is relative. Hyperbolic is not relative. That means, for instance, that the angles of a triangle determine the sides. There's nothing as similar to triangles. Once you give me the angles, the sides are fixed. And the sum of the angles is always less than pi in this world. And here, because I'm working on a sphere, the angles will be greater than pi. And this is also another way of trying to get experimental verification. Gauss tried to measure the deficiency, the angle deficit, by measuring a triangle made up of 3 mountain peaks in southern Germany. It wasn't, his measuring equipment was not able to come up with any clear determination because the experimental error was so large. But here, quantum mechanics, and here we have special relativity. Okay? So it's difficult to marry the two of them together. They're in 2 different spaces. And we know that even if Einstein's expression for the velocities admits to this. If we have v is equal to v1 plus v2, this is the way we would add velocities in Euclidean space. But since we know that we can't get anything more than the velocity of light, because if I put v2 is equal to c, v2 is equal to c, and I multiply and divide by this, I have v1 plus c, v1 plus c, times c. If v2 is equal to that, I've got a c. So I can never get anything beyond c with this type of addition law. Okay? But this type of addition law is satisfied by this function. Tangent A plus B, tangent tangent A plus tangent B, 1 plus tangent. This was noticed all the way back in 1909 by Sommerfeld, who quickly wanted to sweep it under the carpet. Okay? Because this is a fingerprint that special relativity is nothing but hyperbolic geometry. Okay? And we can even generalize this to more than 2 velocities. How? We don't work with v. We work with precisely the ratio of qr plus 1 times this. So v beta 1 would be equal to 1 minus qr plus 1 over qr squared, if we solve for beta 1, plus qr plus 1 over qr squared. And we can continue this and to 3, for instance. And we would come out with an addition law for 3 velocities of the form beta 1 plus beta 2 plus beta 3 plus beta 1, beta 2, beta 3 divided by 1 plus beta 1, beta 2 plus the product beta 2, beta 3 plus beta 1, beta 3. This is the way they would combine if we have 3 velocities. We couldn't get this from that. We could get it by noting any beta would be equal to 1 minus alpha 1 minus alpha 2 minus alpha 3 over 1 plus alpha 1, alpha 2, alpha 3. And reinverting that, we get that. So this means this is means that we can generalize this to any type of velocities. So what are these things? Well, we don't really know what they are, but we can do so from the same way that we look at the action in quantum mechanics. Now, as I said, instead of cosine, we have S of theta equals R theta minus and we want this to be stationary, and the condition is ds dt theta is equal to R minus equal to 0. Okay? And we can divide through R over T is equal to sine theta, or leave this here. Sorry, this is divided by. We go back to the first equation here, and we notice that this must be x prime. And if I divide x prime by t, that's not a velocity. Because I have a frame, stationary frame, divided by moving frame. And I already know that this is the velocity, x divided by t. Since the primes are equal to the unprimes, the velocity is the same because it's an inertial system. So I know this is the velocity. What is this? Okay? Let's find out. So, if I go back now and put this back in here, I have S equals to R. Theta is sine of R T minus T. And if this is cosine, then the other should be we have cosine squared of theta minus sine squared of theta equals to 1. Okay? So this should be the square root of 1 plus theta squared. No. Sine is x prime over. Okay? That's what I get for that. And from all this, what comes out is that if I define omega here, omega is still mc squared divided by h bar. So I put that back in here, which is mc squared divided by h bar. And here, this will be c h bar or mc. This is my lambda. That's the units between the points on the line. And r are the number of intervals I have. So this is distance. So I have distance in one frame, time in another. And that cannot be velocity, but is in fact momentum. So I have r lambda over T is equal to P over M. Okay? And T, the second one here, I come out with T prime over T is equal to omega. Multiply both by h bar. This becomes mc squared, and this is the energy divided by mc squared. Whereas the lengths involved are r over T equals P over M. And if I form the ratio of the two, what do I get? I get P squared, C squared over E. And that, we know, must be equal to the velocity. And if I put that in, I get R lambda over T primed, T primed over T, and this is just V. Okay? So the idea that this should be equal to the momentum means that sine of theta will be equal to 1 minus beta squared and beta. The energy is related to cosine of theta, which is equal to 1 over. And when I place these two inside here, I have a limit on how fast the particle can travel. It cannot travel any faster than V equal to C, otherwise this blows up. So implicitly and explicitly, the Lorentz transform takes care of the fact that the particle, if I measure it from a Euclidean point of view, cannot surpass C. Okay? But from a, by looking at the hyperbolic area system, it can go as fast as it wants. And the two quantities, the difference in the two, PC squared, is equal to M squared C squared, which is the relativistic conservation of energy. In the elliptic case, energy is constant. In the hyperbolic case, mass is constant. Okay? I guess I'll stop here. And any questions?